Hello all. In these sessions, we'll discuss the sign conventions of that shaft when it is subjected to clockwise torque and anti-clockwise torque. Okay. Now, if you look at the arrangement, this is the direction of torque. So when we apply right hand thumb rule, then what will happen? The curl finger will denote the direction of rotation of torque, and that thumb will denote the direction of torque. Now, if you apply the right hand thumb rule, then if you look at this side, these are the curl finger and this is the direction of shaft. So when shaft is rotating in anti-clockwise direction, okay, so at that time what will happen? So the torque will be negative. Okay, the thumb is towards the shaft and the direction of rotation is anti-clockwise. Similarly, when we consider the direction of rotation, if we apply again right hand thumb rule, and when the curl finger will denote the direction of rotation, it will be like this. And when thumb is away from the shaft, then direction of torque and angle of twist is positive. So this is the thumb rule which we can use to define the direction of shaft. Okay, so for torque and angle of theta, always apply that right hand thumb rule. So by applying that right hand thumb rule, we can define the direction of torque, whether it is positive or negative. Okay, so based on these conventions, we'll solve some examples. Okay, so let's consider this example of shaft. A step shaft is subjected to, it is made up of aluminum, steel, and bronze material. Okay, this shaft is subjected to torque of 1.5 kilonewton meter. Now look at the direction. This curl finger will denote the direction of rotation. It is anti-clockwise, and 1.5 kilonewton meter at point D and 4 kilonewton meter at point B. Now the material is aluminum, steel, and bronze. The length of shaft is given 3 meter, 2 meter, 1.5 meter, and they have given the shear modulus 28 GPa for aluminum, 83 GPa for steel, and 35 GPa for bronze. And we have to calculate maximum shear stress in each material and angle of rotation at free end of the shaft. Okay. So if you consider the direction of rotation at bronze, what will happen? This is the direction of rotation. This is the curl finger, and the thumb is towards the shaft. That means the torque will be negative. Okay. So for section at bronze, we have section CD. So we have torque negative, which is minus 1.5 kilonewton meter. For section BC, again, the torque is negative. The curl finger is in the direction of rotation and thumb is towards the shaft. So if you apply that right hand thumb rule, again for section BC subjected to same torque of minus 1.5 kilonewton meter. And if you look at that section BC, again it is minus 1.5 and it is minus 4. So it is total minus 5.5 kilonewton meter. Okay. So these are the torque at section CD, at section BC, and at section AB. So we have to first determine the value of torque at various locations. Then length is available. For aluminum, we have length 3 meter. Then modulus of rigidity 28 GPa. Then diameter is available for aluminum 100 mm. Similarly, for steel, length is 2 meter. Modulus of rigidity 83 GPa. Diameter is 75 mm. And for bronze, length is 1.5 meter. That is 1500 mm. Then we have modulus of rigidity 35 GPa and diameter 75 mm. Now we have to calculate shear stress. So we can apply that equation. Tau max is equal to torque into radius upon polar moment of inertia. So radius is d by 2. So we can put that value, or we can define that tau in terms of diameter 16 into torque upon pi d cube. If you just put that value, r is equal to d by 2, then you will get this equation. So tau max shear stress for aluminum is 16 into torque is available 5.5 into 10 raised to 6 upon pi into d cube. Diameter is available 100. So you'll get shear stress at aluminum 28 megapascal. Similarly, shear stress for steel you will get TR upon J, T into d by 2 upon pi by 32 d raised to 4. So again, that equation will become 16T upon pi d cube. So for steel, if you put all these values, then for steel you will get shear stress 18.1 megapascal. Similarly, for bronze, if you put that value of torque and diameter, then you will get that value of 16 into torque pi d cube, 16 into 1.5 10 raised to 6 Newton mm upon pi into diameter is for bronze 75 mm. So you get that value 18.1 megapascal. So we can calculate shear stress by applying that equation. Tau max is equal to torque into radius upon polar moment of inertia. Now next, to calculate angle of twist, so what do we have? total angle of twist is nothing but angle of twist for aluminum plus angle of twist for steel plus angle of twist for bronze. So you can put that value of torque. You can take that sign. Torque is negative. So minus 5.5 into 10 raised to 6 into length 3000 mm upon G modulus of rigidity for aluminum 28 into 10 raised to 3 megapascal. J value polar moment of inertia pi by 32 d raised to 4, that is pi by 32 100 raised to 4. Plus again we can take torque for second steel minus 1.5 into 10 raised to 6 Newton mm, length 2000 mm, then G value 83 into 10 raised to 3 into J value polar moment of inertia pi by 32 75 raised to 4. Again for bronze minus 1.5 into 10 raised to 6 Newton mm, length 1500 upon that G value 35 into 10 raised to 3 megapascal and J value is pi by 32 75 raised to 4. So if you put all these values, then you will get theta minus 0.0922 radians. You can convert that value into degree. So minus 0.922 into pi by 180, you will get that value 5.28 degree. So that based on that sign, if it is clockwise or anti-clockwise, you can define that position. So we have theta value 5.28 degree for this arrangement. Okay. Now second part, suppose we have again step shaft is given, which is made up of steel and bronze. Okay, and the value of permissible shear stress is given. Okay, and the question is calculate that value of torque. Okay, now look at the direction. One is clockwise, second is anti-clockwise. Okay, so based on this, if you apply again right hand thumb rule, this direction is clockwise. That means shaft is away from the component. Okay, this is the direction of torque and this is the direction of curl finger will define the direction of torque and this is the position of torque. Okay, so if that right hand thumb is away from the shaft, then it will be positive torque. If it is towards the shaft, then it will be negative torque. So torque at bronze is plus T, torque at steel is minus 3T. Okay, because overall will be this overall torque will be 4T minus T. Okay, so it will be minus 3T. Okay, that torque we have to consider. Okay, now next we can take that value of tau max TR upon J. Radius is d by 2, J pi by 32 d raised to 4. So tau max is equal to 16T upon pi d cube. So we'll get torque value for steel 3.392 into 10 raised to 6. Okay. Similarly for bronze, what we have for bronze, we have that T value TR upon J, that is 16T upon pi d cube. So T is 0.55 megapascal is equal to 16 into torque upon diameter is 40 mm. So you can get that torque value 0.691 into 10 raised to 6 Newton mm. Okay. Now overall value at steel we have minus 3T, at bronze we have plus T value. So what we can write? We can write theta value is equal to 5 degree, that twist total rotation is given 5 degrees. So 5 degrees is equal to, again we can take that 5 degree into radian, 5 into pi by 180. So that value will be in radian is equal to minus 3T into length is 1000 upon G value 80 into 10 raised to 3 megapascal into J value pi by 32 60 raised to 4. Okay. Similarly, we can take torque value for bronze, it is positive, length 1500 mm. Then G value modulus of rigidity for bronze 35 GPa and J polar moment of inertia pi by 32 into d raised to 4, that is pi by 32 into 40 raised to 4. So if you put all the values, then you will get torque based upon angle of rotation, which is 0.6187 into 10 raised to 6 Newton mm. So in this way, we can calculate that value of torque based on this arrangement. Okay. So thank you all.